people stuck out in the snow, in the snowy boonies of Tennessee. All right. Yeah, I see people. Yeah.
My driveway will be like.
Oh yeah, mine too. Yeah, I really should have scraped it, but
Well, that was like the same height as a water tower. Like I live like on a very top of the hill, so like my dad's like the only way we're getting anywhere.
wow. Okay, so we're going to be talking about the compounds. Again, we're going to talk about how elements combine. We're going to develop a language we need to discuss these. And this is going to be part language, part a little bit of math, and partially like a scientific understanding. Okay? And you sort of need every single one of those to understand everything. So the electron arrangements in your octet rule. So one of the reasons that elements form compounds is so they can share electrons in arrangements that will make those elements more stable. Okay? Think of this as lowering the overall energy when they combine together to make these compounds, right? If it was the reverse and it would make something that was higher energy, that would tend to, well, explode. So that's the sort of thing you see when they make things like explosives, okay? The exact location of any given electron outside your nucleus is incredibly difficult to actually determine that. They're very, very light. They actually pop in and out of existence. And so they don't even need to go through objects to get several. Okay? They can actually like just now they're over on the other side. Right? So in any given like lab or place, we actually just call this an electron cloud because we can't actually identify the exact location of of electrons. So we just have to identify where you're likely to find those electrons, which is called the electron cloud. Nose is leaking because I just came in out of the cold. All right. So now again, those electrons, they are charged. They're constantly in motion, so they are going to possess energy, and they're extremely light. Does anybody remember what sort of weight we're looking at in terms of electrons versus protons? So if a proton was a 1 mass, which is like atomic mass units, okay, then the electron would be about 1/8,000th of that, right? It weighs almost nothing, okay, in comparison to the protons and neutrons. Now, does anybody know what the size of the nucleus is? I know I keep showing you these pictures of atoms with the nucleus, right? The nucleus about that big, like a sort of tennis ball looking thing, right? And then the atom is like, has this shell thing, that's the electron cloud. And that thing looks like a maybe basketball, right? So you probably think nucleus, tennis ball, then basketball for the whole atom, right? No. So if you were to take a baseball or a tennis ball, they're pretty similar in size, depends on the atom really. And you were to put that in the exact center of the football field, then the goalposts would actually be to the first orbital, the smallest orbital of electrons. The first place you'd start really seeing all the electrons gather. Okay? And so that's the sort of difference you'd see, actually. I can't do that up here because then your nucleus would be so small you couldn't see it, right? And so the diagrams don't make any sense for me to actually put in perspective. Okay? But keep in mind that these electrons are taking up a tremendous amount of space. They're 99% of the volume of the atom, whereas they are less than 1% of the mass. Okay? They're more like 0.1%. And so they're very fast moving, weigh very little. Any energy input is going to cause these things to zip around. Okay? And it's so fast that you won't be able to follow it with the best cameras. That's what the speed of electricity is, in fact. How fast electrons can move around. Okay? Which is very fast. All right. So again, electrons are only going to occupy certain energy levels. These would be like the steps on a staircase. Whenever you're going up steps, you can only occupy certain energy levels. You don't put your foot on air and then go whoop to the next step, right? You can only occupy the energy levels of the steps. Okay? Same thing happens to electrons. They can only occupy very specific energy levels. Congratulations, this is the intro to quantum mechanics. Okay? So when you get asked, what did I learn today? You can go, I just learned a little bit of quantum. And sound really impressive, okay? There you go. Quanta as in broken up into steps, right? Quantum as in broken up into steps. Okay. So in general, your electrons can occupy your lowest energy level first. It's much like stacking up something in your toy chest when you're a kid. You probably tried to stack them all into like one little column. And then what happens? Well, they fall down, don't they? Because that's higher potential energy than the bottom layer, which would be lower potential energy. Okay? And so your lowest energy level, this is always going to be found closest to the nucleus in these atoms we're thinking about right now. And basically, lower energy level is closer to the nucleus. Okay, it's very similar to the planet, which has gravity, right? And we're up higher now, third floor, so we have more potential energy, don't we? Why don't you want to just jump out the window up here? Too much potential energy. When that potential energy gets released downstairs, it's going to really hurt, right? And so don't jump out the window up here. Could you jump out the window on the first floor? Yeah. Wouldn't even be much of a problem, would it? Because a lot less potential energy. Okay? And so you have a lot less energy to release when you hit the ground. Okay? Now, unlike our staircase, the energy levels do get closer together the farther you get from the nucleus. And so the further you get from the nucleus, these energy levels start shrinking. So it looks more like this. It looks kind of like a very strange staircase, right? Funny enough, if you actually were to make the building clear, this is kind of what the staircase in this building looks like. Because it starts way down there, right, for ground level. So the first level is really big. Right. But this would be what the energy levels in looks like. And what this would look like is these are further from the nucleus each time you go. Okay? And so as you get further from the nucleus, you get more space and you get less pull by the nucleus, right? And so you have less difference for being here versus here than being here. Being real close, law of energy, very, very strong attraction, right? Being further away, not much difference as you go. All right, so these are your energy levels, by the way. You may notice that it goes like 1, 2, 3, 4, 5. There's also a pattern up there that goes 1, 2, 3, 4, 5 as you get further away from something. And so these directly correspond to them. Okay? These energy levels here are the same as the periods up there. And in fact, if you just look at a very simple explanation for this, you can actually call the periods up there energy levels. You'll catch me doing that quite often. Okay? And I may have done it already. If I did, that's why. Those are energy levels going further and further from the nucleus as you fill in more electrons around the nucleus, right? Okay. So the maximum number of electrons that can be found in any given energy level is going to be calculated with the formula 2n to the second power. So n is going to be the number of the energy level. In the first energy level, that would be the one on period 1, where we have hydrogen and helium, right? You would have, you put 1 here, right? And this is to the second power, so still 1. 1 times 1 is 1. And then you multiply it by 2, and that's 2 electrons can exist in that. Hey, how many elements are up there? There's 2, isn't there? Why is there 2 elements up there? Well, you can only fit 2 electrons in the space. So you can only fit 2 things up there. Okay? We get to the next one. That's the second energy level, second period. And so this is going to be 2 for the energy level, period 2, right? And we take 2 times 2, and that's 4, isn't it? We do 1 more times 2, and that's 8. And so what do we end up getting? Well, 8 electrons can fit in this orbital space. Okay? And this space, you can fit these electrons. How many elements are up there? 8. Yeah, we got 8 again. So that's actually a direct reflection of the amount of electrons you can fill in on these orbitals. Okay? And that's how the periodic table is actually organized. That's why you get these repeated patterns every 8 for those first 2 periods. Okay? And you get very nice, neat patterns, right? Because you can fit 8 electrons, you can fit 2 electrons in the first one. And so that gives you the pattern. When you go to the next one, if you tried to fit the 9th one in that orbital, won't fit in, you have to go up to the next orbital, next energy level, right? Which is the next period. All right. Now, 3 is where things get a little weird, okay? And so I want you to start thinking of these orbitals, these energy levels. These are like rooms in a building. And so you have these desks, right? And at each desk, we can have a student, can't we? And that's how students are organized. Within those desks, we can also have higher or lower energy levels, can't we? First floor has lower energy levels, doesn't it? Second floor has higher. Third floor has higher. Okay? And so you can kind of think of this building as like an inverted pyramid. Okay? The bottom has to be real small because you don't have a lot of space there. Okay? It's filled up with a lot of other stuff, just like we don't have space on the first floor for classrooms, do we? We have very little classrooms because all the administration has to be there. Okay? Second floor, more classrooms, but still a lot of administration, right? Because administration is taking over the world. Bureaucrats run everything. Don't tell the administration I saw bureaucrats. Actually, they're very nice. But they are technically bureaucrats. Okay. And so we get to the third floor on this building, right? Lots of classrooms, lots of labs. Probably a majority of classes end up on the third floor for you guys. Okay? In this building at least. And so that one right there is going to be where we're, more space. Now, notice though, not all of those classrooms get used for everything. There's one over there that doesn't get used right now. It's empty, right? There's one over there it's empty as well. It's a lab, isn't it? And so all those labs, they're kind of awkward spaces, right? And they're higher friction, higher energy spaces, okay? Literally higher energy because they have gas lines in them. And a lot of electricity and water and all that, right? So literally higher energy in some cases. And so when you get to the third energy level here, that third period, okay? You notice the third period on the periodic table only still has 8 on it, right? But when you get to the third energy level, you're actually going to create, 3 times 3 is 9, times 2 is 18. Does that sound familiar? That's the number going across, isn't it? That total number that you end up dealing with until you get down to, of course, the bottom here with the Lanthanide series. So at energy level 3, we create 18 spots that you can put electrons. Okay? There's 18 places that electrons can fill in, like an 18-desker, right? And this right here is just so awkward. Notice nobody ever sits at that desk over there unless they have to, right? It's only when everything else is full that that desk gets filled up, right? And then even when we're doing labs, if we do anything that is just like, hey, let's do some quizzes or review or something, we're always moving into here, aren't we? We try to be in here to do those. The only time we don't is when we just can't, right? And so we still don't fill those up if we can avoid it, do we? And so those are the high energy that are still on that same floor, right? They're high friction. They're a problem, right? And so these right here, 8 of these are fairly low energy compared to the other 10, okay? Those other 10, see that block in the middle that's transition metals? Okay. That's actually the orbitals that we made here. They don't get used until the 4th period because they're so high energy compared to everything else. Okay? And if you ever look at these, you can look them up. I'm not really going to go into a deep dive on this. It's just not necessary for most of you. But if you're interested in it, we actually know what these orbitals look like. And the s and p orbitals, I'll show you a bit. The d orbitals, I won't even bother because they're really weird shapes. Like one of them looks like a clover, 4-leaf clover. One of them looks like a donut with a little rod through it. They're very strange shapes. They're very awkward, and they're higher energy than the other orbitals on the same period. Okay. And so, for example, the orbitals getting used up when you were talking about titanium, we're just starting to use up the third period, what are called d orbitals. Okay. Those are the ones that are made on the third period. They're just high energy compared to others. So they don't get used up as fast. All right, so these right here are going to be your group numbers, different elements, the total numbers of electrons, and the numbers in each of these energy levels. Notice again, you fill up the energy levels starting from the smallest one, right? The lowest number energy level, because it's the lowest energy. Okay? And then you go to the higher energy levels. If you were to do it the other way around, these are just empty space electrons can be in. Okay? The best idea to think of these in your head, if you want a vision to think of, is if everybody played with those iron filings with magnets. You know, there's the toy with the iron filings, and you can move the magnet, and it like creates the little and rings and stuff. No? No. Okay, that's incredibly disappointing and sad. God, that's. I need to talk to your parents. They need to take you all on a field trip. Anyways, I guess the other way I could do is a light flashlight. You know how you shine a flashlight against the wall and it makes like patterns on it, and it's like bright, darker, really dark, bright, and they're like these random looking to you patterns. That's actually a very similar concept. Okay, as what you're seeing here, they're sorting themselves out depending on the position. Okay. So anyways, that's what these orbital positions look like. They're actually just empty space that the electrons are going to be attracted into. Okay? And so if you put electrons in a higher energy orbital, they're just going to fall down into lower energy one because they're pulled down into it. Okay? Just like if there was no floor right now, you'd be pulled down to the ground, right? Okay. You all are going to have nightmares. Dr. Clausen traumatized me, so now I think about falling out of their floor all the time. Okay. Notice that the group numbers are directly related to the numbers of electrons that are in that outer orbital. Okay? And the reason this is like this, that we've done this, is that the electrons in the outer orbital are always the electrons that are going to do chemistry, right? So, for example, if you were trying to shake somebody's hand, you would not reach into their mouth. I would hope. Okay? Why don't you interact with the stuff inside the person when you try to interact with them? Because you would hurt them going into the inside parts, right? It's very, very graphic, nasty, and we think of it as graphic and nasty because you have to go through stuff to get to it, right? So the electrons are just like that. If you were to try to go through the outer electrons, right, you'd have to penetrate through and get to the inner electrons. And they're going to be very, very difficult to interact with. Okay? Now, having said all of this, there's some interesting little side notes that are kind of trippy, like, I'm going to call them weed conversations, but really they're like late night conversations. You can go, oh man, that's real trippy. So, you all know the types. And so one of the trippy things is you are 90-something% empty space. Okay? You're almost all empty space. If we didn't have these electrons being negatively charged on the outside repelling each other, we would just pass through objects. Most of us would just pass through. Like you put your hand on the desk, you are not touching the desk with your nuclei. Your nuclei don't come anywhere near the nuclei of the desk. Okay? So all your mass doesn't come near it. But what you do is your electrons start repelling the electrons of the desk. Okay? And that's what you're feeling when you're touching things. Is you're actually having the electrons the outside of your atoms repel the electrons on the outside of the disk's atoms. Okay? And then they get to be these very, very large forces that are doing these repulsions. Okay, so the same thing happens within an atom, of course. The lower energy levels are going to repel the outer energy levels electrons, and so they can't go through. Okay? All the chemistry is always going to happen on that outer shell of electrons, that last energy level. Okay? So the outer energy level, that's where all the chemistry happens. How many electrons are in that outer shell? That determines a lot of how this is going to react. Okay? If it has a very small number, it's going to tend to lose those electrons. If it has a larger number, it's going to tend to gain electrons. So that has full energy level. Okay? A full shell. And that's why we have the noble gases all the way over there, right? The end. That are noble because they don't interact, right? They don't react with things. Okay? They already have full shells. Okay. So, being able to locate the number of electrons present in an energy level does provide us insight into how the atoms and the elements in a period or group are related to each other. That number of electrons in that outer orbital tells us most about what it's going to be in terms of chemistry. Okay? All the jewelry metals react very similarly because they have the same sort of numbers of electrons in their orbitals. Okay? All of group 1 reacts very similarly because it has one electron, very easy to lose. Okay? And so they all interact very, very similar. Elements in the same group are going to, again, have the same number of electrons and that highest energy level. That's what makes them in the same group. Right? Boron and aluminum are going to have 3 electrons in their highest energy level. That's why they're group 3A. 3 electrons in that highest energy level. Okay, so the highest energy level that contains electrons, the exact name for this is actually typically the valence shell. Okay, it can also be called the valence level, the valence energy level, but valence meaning outer, right? It's the outer shell. The electrons that are in it would be then the valence electrons. They're the electrons that are in the valence level. Okay. The valence electrons are going to be farthest from the nucleus, so they're going to be the least tightly held, and they're going to be the easiest to interact with because they're on the outside. So all the chemistry, there you go. That is 99% of the chemistry that you will ever see on anything. Okay. Now, these electrons will combine when elements make compounds. They're going to do so that they can share electrons and thus get full orbitals, full energy levels. So they can fill that outer energy level up. Okay? And it's kind of like I have $1, my friend has $2, we want a cheeseburger. Let's say the cheeseburger is $3, even though. And so, is it going to work for me to go to the Sonic and, hey, I have $1? No. Is it going to work for him to go? $2. No, but if we combine them, we can get a cheeseburger and split it, can't we? Okay? And so the elements are doing that. They're combining to get their cheeseburger. You can tell I'm hungry. Now, the groups columns in that periodic table, they're going to indicate your number of valence electrons in those atoms for your main group elements. Okay? They're mostly focused around main group elements because that's the majority of chemistry that happens around you. Right? As we go lower, it's still similar rules, but you got to remember that we're going to start having things like D and F orbitals. We're going to have these weirder orbitals that don't get used right away, okay? And so it's going to start looking a little bit more strange. But that's also why the chemistry of that stuff down there gets a little more strange, okay? So the periods, these are going to indicate the outermost energy level containing electrons. So period 1, valence shell 1, right? Period 2, valence shell has 2. Okay, that's where the valence shell is. So energy level 2 is the valence shell on the elements in period 2. Energy level 1 is the valence shell on period 1. Does that make sense? That's telling you the outermost energy level. Okay, and so this is what that periodic table looks like. We're just going to look at the main group elements right now. And so this right here is the main group elements. And you notice here, those are that 1 through 8 for the electrons, right? We have period 1, energy level 1, has 2 electrons that can fit in. Energy level 2, we have 8 electrons that can fit in. Okay? Okay. Now, this is where the chemistry gets a little weird, which is period 3. Okay? So when we get to energy level 3, period 3, we have 8 electrons that will actually fill up the space. Okay? But we have space for 18 electrons. Right? There is the space. You could put 18 electrons around these things. And that's why you get really weird stuff that has more than 8 electrons around it in this period. Okay? For example, the big one would be phosphate. If anybody's ever had a biology class, phosphate might sound really familiar. That's because it's the backbone of DNA. Okay? And so phosphate has more than 8 electrons around that phosphorus. It's on period 3. It has the space to fit it. Okay? Doesn't happen as often. You have to have some kind of special circumstances to get that sort of stuff happening. Because, again, it's higher energy to put those extra ones in. Okay? You have to pay more for it. All right. So again, the elements in group 8A, these are called the noble or inert gases. They're on-reactive under all but the most extreme conditions. You would not normally see those react, and that's why they're known as noble. They're too snooty to interact with everybody else. Okay? You can tell a lot of this work was done by Americans. The nobles don't interact with anybody. Okay. Most atoms are going to react with other atoms to achieve 8 electrons in their valence shell. This is what's referred to as the octet rule. I'm going to teach you the octet rule because it pops up everywhere in chemistry. I absolutely hate the name. It is the dumbest naming you could come up with because it only works on one period. Octet meaning 8, right? Like octopus. So period 2 is the only period where it actually holds completely. Okay. I personally like to call this noble light. Okay. Go to noble gas. That's what it wants to be like. Right? There you go. That's my rule. Dr. Clausen's rule. Noble light. Okay. Everything wants to be like a noble, right? So you always are moving towards your nearest noble. By the way, one of the blind spots that students tend to have when we're first learning this, can you only go to the right on the periodic table? Can you only gain electrons? No, you can lose electrons, right? So if the nearest noble is going left and going up a period, that's what metals do. They lose electrons so that they can be like the nobles that are in the previous energy levels. Okay? And so you can go either way. You can gain electrons to be like the noble on the same period, or you can lose electrons, be like the noble on the previous period. And atoms don't care. They're not like, oh, I'm going up the periodic table now. Better not do that. Mendeleev said no. So anyways, the different modes of achieving valence octet are going to lead to different kinds of compounds. So losing electrons, gaining electrons, whether you share electrons instead, so you can get the full octet. There's some really unique things where you have like boron, and it will give 3 electrons, but still kind of keep them. So you get some really fun stuff sometimes. If an atom gains or loses electrons to achieve an octet, the new formed particle is going to be on unequal numbers of protons and electrons. Remember, protons are in the nucleus. They're not going anywhere. If you change the number of protons, you actually change the number of the element, don't you? So you can't have a carbon that has a different number of protons. Okay? You can have different numbers of neutrons, not protons. And so if we lose 1 electron out of one of these, well, it's going to become charged, isn't it? You're still going to have the same number of protons, aren't you? But now you have 1 less negative charge. Kind of like if I lost a negative debt, right? I'm going to have more money. Okay? Do money relations work well for you all, everybody? Everybody understands their bank accounts well, right? I think that's the most universal ones I can come up with. Okay, so if we gain an electron, that's going to give us a negative charge. If we gain 2 electrons, that's going to give us a negative charge of 2, isn't it? 3 electrons would give us a negative charge of 3, right? So the more extra electrons you have, the larger the negative charge. These things with negative charges on them, we call them ions, but that doesn't tell us whether it's positive or negative yet, does it? And so we call that an anion. Okay? And the easiest way I tend to think of these is cations are the positive, anions are in the negative. Okay? If I have my picnic and I have cats show up to my picnic, most people that's a positive. If I have ants show up to my picnic, most people that's a negative, right? And so an anion is a negative. You can go either type of ant, the ant that crawls along the ground, or the ant that pinches your cheek. Either one, depending on how much you like your aunts. Okay? Okay. And so anion, negatively charged particle, it's going to be where we have gained an extra electron, right? So we have more electrons than we have protons. So what if we lose an electron? We can lose multiple electrons on some of these. And so this is going to be a cation. Okay, it's going to lose electrons, so we have a positive charge. Right? Again, you don't gain or lose the protons, though, because they're in the nucleus. They're not going anywhere. They're too heavy, and they're in the center. Okay, now, the last thing we need to talk about is, what does iso mean? Like isolated, is there other isos, though? Isosceles, triangle. It means equal. Okay? So, isolated, technically, you're equal to. Everything's equally isolated around you, right? I'm sure that's the same root word. I wonder how that got there. But iso means like isotonic means same concentrations. Isoelectronic means same charge, same number of electrons. Okay? And so isoelectronic to a noble gas would mean it has the same electron configuration as a noble gas. Same number of electrons in that outer shell. Okay? And so if I was to say I have a hydrogen, it's isoelectronic to helium, what I'm telling you is that I have a hydrogen with 2 electrons, right? And so it is a hydride, which is a negative hydrogen. Okay? If I have an oxygen and it's isoelectronic to neon, then I have a oxygen that has gained 2 electrons, so it's the same number as neon. Okay. So let's talk about some of these trends in ion formation. You're going to notice that, again, everything wants to be like a noble, right? So the things in group 1, 2, and 3 tend to lose electrons because it's faster going to the left to get to a noble. Okay? And so the group at 1, they're going to tend to lose 1 electron. So they're isoelectronic to the noble. Okay? Group 2 tends to lose how many electrons? 2 electrons. You got it. Because 2 electrons gets it isoelectronic to a noble. Group 3 tends to lose 3 electrons. Again, isoelectronic to a noble, right? Okay, what do you think about group 5A? Which way is faster now? To gain. Yeah, because 4's the middle, right? No, sorry, skip 4. Not as simple. 4 is your middle, right? So anything that's higher than 4 for the groups, it's going to be faster to just gain the electrons then. Okay? And so 5A, you're going to gain 3 electrons to be isoelectronic. 6A, 2 electrons gained. 7A, 1 electron gained, right? Okay. And so typically you would find these ions, like we talk about chlorine right there. See the Cl right next to the noble gas? Okay. If we talk about that, it's typically going to have a charge of -1, isn't it? because it wants to gain 1 electron to be like a noble. Okay, and so that's going to be the typical bonding patterns too. Chlorine typically makes 1 bond, so it can gain 1 extra electron. Okay? Oxygen typically makes 2 bonds, so it can gain 2 electrons to be like a noble. Oxygen's found as an anion as an O2 minus because it wants 2 electrons to be like a noble. Okay, so the transition metals are one of those places where things start to get a little complicated, okay? And it's where we start getting things like these really easy rules. Keep in mind, science rules are rules as in rules like you follow for the traffic, okay? Can you never pull into the other lane? No, it's a rule not to pull in the other lane, right? Especially oncoming traffic. But if things go wrong, you pull in the other lane. Okay? Sometimes it happens. So, science rules are like this. The things that should be unalterable, at least under the conditions that are stated, are what are called laws. Okay? They're scientific laws. They're not referred to as rules. So, it's actually really funny because there's been this like string of breaking different rules and showing examples over the last like 3-4 years. That's really, really, I mean, it's great for science. But it's kind of funny because it's like every paper starts with, your teacher taught you these rules. Come on. They're rules as in guidelines, okay? They're what's usually going to happen, not you can't not do this. Don't take it out on me. Actually, send me the publication if you do that, okay? I think that's cool. I love it. That's how science progresses. All right. So it's some transition metals are going to form more than one ion. It's actually not possible to determine the charge of the ions formed by that transition metal from just their group number. You can't just go to like group 7 there, 7b, and go Mn is going to make this number of electrons every single time, period. Okay? Polyatomic ions are going to consist of groups of nonmetals. They're going to form an ion together. And so the charge is actually going to be for that entire group of those atoms that are forming that polyatomic ion. Okay? You're going to see this happen a lot with oxygens, where you have NO something, CO something, ClO something. Okay? And it has quite a few different varieties. Now, this right here is just the common numbers that you would see. See, these are those common numbers we just talked about. This is the majority of chemistry. You end up encountering these. So it does make life a little bit easier. Right here are the transition metals, and so you see that those can have multiple different charge states. It's actually why rust, for example, you may notice rust has all these different colors going on. That's part of what makes rust so various in color. Okay? Is that it has iron 2 plus and iron 3 plus in there. So you can get a great variety. These right here are the most common polyatomic ions. There are more than those, but these are the ones you need to know. Okay? You need to kind of semi-memorize these. You do have a sheet you get on every exam, 1 page front and back that you can bring. Hint, hint for the next exam, and which is coming up. And so what you'll see here is that you need to know these polyatomic ions, what's in them, what the name is, and what the charge is. I would recommend flashcards, which you go through forwards and backwards. Okay? If you don't know these polyatomic ions, one of the things I always want to point out whenever we're doing this stuff is if you don't know the language of chemistry, then you can't really interact much with the problems. And I have a story I tend to tell that gets refreshed every few years, is I have caught 7 people cheating on chemistry exams that I went ahead and graded first to see what happens, just because I'm curious. I let them finish up their exam, took a picture when they weren't looking. Yes, I can do that too. And, you guys can use the phones under your desk, right? I can see under the desks. So I can go. Okay. And so, of those 7 people, none of them made above a 20% on the exam they cheated on. Not a single one. Okay. And so I've talked to them. If it was something really serious, I put that through to administration. But the fact of the matter is, if you don't know the language of chemistry well enough to know what the heck you're being asked, then there's not a lot you can do, even if you look the information up, right? Because it's like trying to take a test in Greek or a language you don't understand. It doesn't matter if you have a book if you don't know what's being asked. Okay? So that's always the entry level. If you know the language, you're typically going to get somewhere like a 70% on the exams. Okay? With nothing really else. You can at least interact with every question and at least eliminate options. Okay? After that is going to be where you want the math and the understanding of concepts. I would rank language, understanding concepts, then the math. Okay? And for reference, no, nobody ever has failed an exam from one question out of 30. So that's what I always get is people get super concerned and concentrated about like 3 or 4 questions, right? And oh, that question was so hard. How could I ever accomplish that? You, out of a 30 question exam, you need to fail the exam. You need like 15. You need 10 questions wrong, right? About 8 actually, but like you don't fail it off of 2 or 3. Okay, that just isn't possible. And so keep that in mind that like you can. There's parts of this that you, if you don't know everything, you can still do well in exams. You just actually have to give it an effort, and you have to have some idea of the language and concepts, right? Okay. So, anyways, these right here are some of the different polyatomic ions. What you'll see here is it's mostly going to be anions. There's only a few cations that you need to know. This is one of them. This is called hydronium. This is actually how acid appears in water. Okay, it's going to become really important in later chapters. This right here is actually the basic form. This is the hydroxide, commonly found in antacids. In case you're wondering, this right here is baking soda. Okay, that's bicarbonate. This is the rest of those, and that's the whole list of the ones you'd want to know. Notice there's phosphate. These phosphate groups are joined up into a chain. That makes your ATP, triphosphate, your ADP, diphosphate. That also makes your phosphate backbone for your DNA. Okay, so let's talk about naming ions. First off, how do you name the metal portion? So the metal portion just gets the normal name followed by ion. I know, such a tough one. Okay, so if it's the main group elements that you know what the charge is all the time, that's all you have to do. You're done. So for example, sodium ion, okay, calcium ion, potassium ion, etc. Cesium ion, you got the idea. All right, so the next part is, well, what if we don't know the charge every time? Well, then you have to specify the charge, because there's a difference between having Fe2 plus, iron 2 plus, and Fe3 plus, iron 3 plus, okay? They have different chemical properties. They look different, actually. They are different, right? And so you have to specify that using a Roman numeral. And so, for example, Fe2 plus, this would be iron. Fe is iron. And then it has a 2 plus charge, so we put parentheses, Roman numeral 2. If that was a 3 plus charge, what would we put here? 3. Yeah, Roman numeral 3. Does everybody know how to do a 4? Single line, then V, right? 5 is V, and then 6 is V, then single line. Okay? Everybody got that all right? Okay. Now, you typically are not going to get past a 6, though there is an incredibly important pollutant called hexachromium, which is a 6 plus charge chromium. If you ever want to see Aaron Brockovich as a Imagine documentary over it, you know what I'm talking about, imaginary documentaries. They dramatize it. Okay. For nonmetals, the suffix "ide" is going to be what replaces the last few letters in the name of the element. You've already caught me doing this a few times. For example, chlorine goes to chloride. Okay? Fluorine goes to fluoride. Sulfur goes to sulfide. Right? And that tells you that's the negatively charged anion. Okay? Even hydrogen, by the way, if you were to do hydrogen as a negative ion, would be hydride. So, still the same rules. Now, the polyatomic ions are going to end in 8. Most polyatomic ions are going to end in 8. Okay, this is going to be the most common one. It's typically the one with the more oxygens. The ending "ite" is going to be used for the related ions that have one fewer oxygen than the 8. So if you have carbonate that has the CO3, if you were to have an "ite," that would be things like if we were to go like sulfate, that would be SO4. If we were to go sulfite, that would be SO3. Okay? And so see, one less oxygen, that's the "ite." Easy way to remember that is I ate the whole meal versus I took a bite. Okay? So there are some special ones that have special names. There are exceptions to this convention. That's why I call this a semi-memorization, right? Is you kind of memorize a few things, and then most of it's systematic, so you don't have to memorize them all. Okay? And so as long as you know the one with the most common form, sulfate, SO4, then you know sulfite automatically because you just remove an oxygen, right? There you go. These right here are the ones that ignore those rules. This is hydroxide, OH minus, hydronium, H3O plus, and cyanide, which is CN minus. Again, they are exceptions. They do not follow the naming rule. This right here is sodium, the ion, and so this is sodium ion. This is your one that would show up in like table salt, which is NaCl, okay, sodium ion, and chloride ion. Those are the two components of table salt. And here's some different examples of various different ones. This Fe2 plus shows up in things like liver, red meat, etc. Okay, and it's what gives the nice like red color to that meat. Okay, as it's oxidized, actually, as you goes to the Fe3 plus, that's when you lose that coloring. In case you're wondering, there's nothing particularly wrong with the meat if you lose the coloring. If it starts going to other colorings, then there's something wrong. Don't eat that. Okay. So this right here is what's going to be known as an ionic compound. And so here we have the elements as shown on the periodic table. They're neutral forms, right? And so this would be sodium, metal, and this one here would be chlorine atoms, individual chlorine atoms. Okay? Now, what's going to happen is the sodium wants to lose an electron, the chlorine wants to gain an electron, so the chlorine is going to take sodium's electron. Okay? And so sodium is going to end up with a positive charge, chlorine is going to end up with a negative charge. So this is now the sodium ion and chloride ion. Okay? Now, together you may notice that these are positive and negatively charged, aren't they? What happens when you get two magnets that are opposite? They attract, don't they? And so what's going to end up happening is we refer to these as ionic bonds. Calling them a bond is a bit of a misnomer and is a little confusing, okay? All they are is they're just attractions between a positive and negative, right? You have two magnets, they're opposite charges, they're attracted together, okay? When we're talking about ionic compounds, this is going to be a compound that is ionic in nature. Okay, it's composed of ionic bonds. What we're going to see here is these are just going to stack over and over and over. So a kind of easy way to think about this is we're going to just have our chlorine and then another sodium, and then we'll have another sodium over here and chlorine over here. And they're just going to stack over and over and over because they're positive, negative, positive, negative, positive, negative, right? And so that's going to give you those nice salt crystals you can get, the really big ones. If you break that up, you still have the same sort of ratio going on, just positive, negative over and over and over. Okay? Okay. So that is an ionic bond. Please don't get confused by ionic bond. Okay? And ionic compound. So a compound made of repeated units of those ions. Okay? Now, when we're talking about ionic compounds, they're going to have what's called a formula. Okay? Because they're not really discrete molecules like we were talking about with the other molecules. Like, which of these is the molecule? You can't really tell. They're all joined, right? And so any of these, they don't really have molecules per se. They just have what's called formula units. Repeated patterns that clip together. Okay? And so what you're going to have here is a repeated pattern where they're attracted together. And that's going to give you the formula for your ionic compound. In the case of NaCl, that is a 1-to-1 ratio. And so NaCl is the formula for the ionic compound that we know as table salt. Okay? How many NAs are in a table salt grain? I don't know. Lots. Billions. Okay? Many grains. Okay? Many ions. Right? How big can these get? Massive. Right? If you were to call these molecules, then you've seen mountain-sized objects that are molecules. Okay? These can get huge. Very, very large continuous ionic compounds. Okay? A lot of rocks are ionic compounds of sort of a various formula. Yeah. And so, again, you're going to have cations paired with anions. They're going to combine to give you a net charge of 0, because if it was overall positive, it would repel things, right? If it was overall negative, it would repel the negatives. Okay? And so these are always going to give you these formula an overall 0 charge, right? Notice that NaCl, Na plus with Cl minus, right? And so the overall charge is 0. Okay? Now let me make you all think for a second. If I have Mg2 plus, how many Cl's do I have to balance that? Each Cl is minus 1, right? So to balance at positive 2, I have to have 2 negative 1s, don't I? Okay. And so the formula for magnesium chloride would be MgCl2, wouldn't it? So I need 2 chlorides. Okay, now there's a kind of easy way to do this. You can go ahead and write these out. You're going to represent the number of chlorines as the 2 subscript. That's the number of atoms you have in that compound, right? And the easy way to draw these out, you do not draw the charges out whenever you're putting these formulas down. The charges are going to be implied by the number of atoms of, for example, chlorine. Okay? The fact that there's 2 chlorines there tells you that Mg is a 2 plus. Right? And so this is actually the steps to do this process. So let's say I'm giving you, I want aluminum oxide. You got to write out the formula for aluminum oxide. Okay? And so you're going to look at the periodic table. Aluminum is what group? 3. So that's a 3 plus charge, isn't it? Oxygen is what group? It's 2 steps from a noble, right? So group 6, or another way of saying that 2 steps from a noble means it has a 2 minus charge, right? Okay. By the way, you always put the number before the charge because you're actually saying it has 3 positive charges, 3 protons extra. It has here 2 electrons extra, 2 negative charges extra. Okay? So you put the number before the charge. Okay, so the next thing I do is, anybody ever learned cross multiplication? Is that still a thing? Yeah? Okay. Every now and then I get no. I'm like, oh, wow. Okay. All right, so we're going to cross multiply essentially. Okay. So remember that these are like saying this is saying 3 plus, isn't it? This aluminum. This one's saying 2 minus, right? So if we want to get these to balance out their charges, this needs to be a positive 6 and negative 6, right? So they balance. Okay. So all we have to do here is we just get rid of that charge. We rewrite this down here. So Al and then O next to it. And then the number up here for the charge for the oxygen goes with the aluminum. The number up here, that's the charge of the aluminum, goes on the oxygen. Notice you're just cross multiplying. That's all you're doing. See that? Did I lose anybody? No? Okay. Okay. Very important skill. I'm going to obviously ask you a bunch of questions on this because they're really easy questions. So if you get that wrong, please review this. Homework. Okay. All right. Now, how can I predict the number and charge in a chemical formula? So the formula of an ionic compound is going to have a net charge that is 0. That means all the positives and all the negatives have to add up, right? And so the charge of the anion is oftentimes known. It's almost always known because the anions you may have seen are all those ones on the top right, aren't they? And they're all predictable. The cations are not always predictable because you can get transition metals, can't you? And so whenever I'm doing this, one of the things I want to do is I want to look at my anions first. Okay? So for example, if I give you Fe, F3, okay? Well, F3, that's my anion, isn't it? Right? F, fluorine. Okay? Fluorine always wants a charge of -1, doesn't it? And so fluorine is going to give me -1 charges for each. And so again, I'm given this. Okay? Each fluorine is going to be -1, isn't it? I'm going to have 3 of those. How do I balance out a 3 -1 charges? I have to have what charge on that iron then? Positive. I have to have a positive what though? 3. Yeah. Yeah. And so my Fe is just 3 plus, isn't it? Okay. Now note, if I did that way of saying it because it's easier for you to understand, you can actually just reverse cross multiply. So this just goes up here. This one's the negative, right? So, you can just reverse the process. But again, this always has to sum up to that charge, right? And so you always get the opposite charge on the other one, and it has to sum up to give you that opposite charge, okay? Okay, so if we name an ionic compound, the names of the 2 ions are going to be combined. You'll put the cation first. The word ion will be omitted because the other thing tells you it's an ion, so you don't need it. So for example, you've already caught me doing this a number of times. You probably have all done this many, many times in your life. As everybody knew that table salt was sodium chloride? My sodium levels are very high. And so table salt, sodium chloride, it's sodium ion, right? With a chloride ion, okay? And so it's sodium chloride. For many of these, you do not need to specify the numbers for these ones that are the main group elements because you already know what the numbers are going to be based on the periodic table, okay? So you don't have to say it. Sodium chloride, for example, is always a 1-to-1 ratio because sodium's +1, chloride's -1. So you don't have to specify. Now, for your transition metals, you do have to specify because you don't know automatically. What is copper? I don't know. It could be a couple different things, can't it? And so copper, for example, copper oxide, you have to specify what type of copper you have, okay? If you just say copper oxide, that would mean a mixture of them, right? And in fact, that's what you're seeing when you see patina. Everybody knows patina on copper. It's that pretty like blue, greens, various different colors on copper. that's mixtures of copper 1 oxide and copper 2 oxide. And so you get different colorings for them. So this is copper 2 oxide. This is actually a 1-to-1 ratio because oxygen is -2. Now, what if a polyatomic ion is present? Well, the name of the ion remains unchanged. And so this would be, for example, calcium phosphate. Because polyatomic ions are ions. You don't have to change the name. Okay? By definition, polyatomic ions are always ions. So calcium and then phosphate. One of the things I have to point out, they have to be very careful about, and you're going to get tempted to try to shortcut. When you're doing polyatomic ions, you have to keep them as units. Okay? And so it's a very different thing for me to say I have 3 computers versus I have 3 of the parts of computers, right? 3 RAM, 3 CPU. I may not have the whole thing, right? And so when I have a phosphate like this is phosphate, PO4, right? If I have 2 of them, I have to put parentheses around that to keep it all together, and then put a 2 next to it, right? So subscript 2. And that means 2 phosphates. If I was to put just 2 right here and then 8 here, that is not phosphate anymore, is it? A whole different compound. Okay? Okay. Be very, very careful about that. It's a problem that a lot of students run into and then they get messed up. Right? And it messes you up the whole semester if you don't fix it. All right. Because this is the language we're going to use to build everything off of, right? Okay, so nonmetals are going to be combined by sharing valence electrons to achieve an octet. And so each of the nonmetals will share electrons, and this will give them their full octet. The sharing of electrons is going to result in the formation of what's called a covalent bond. Now, because you're sharing the things together, the easiest way to think about it is it's an actual object between you're pulling on both sides of, right? And so it's going to give you something that's very like an actual bonding, right? That you have something physically forcing you to maintain each other. Okay? It's those 2 electrons in the middle that both sides are going to pull on. And so that's a covalent bond. The valence electrons in the bond, they're going to belong to both of your atoms. And so they get counted for both atoms in terms of, are you filling your octet? Okay? Kind of like our buying the cheeseburger. Yeah, we have the total amount to get our cheeseburger down. Okay? When the atoms share, the result is going to be what's called a covalent compound. Polyatomic ions are covalent compounds, actually. Okay? Another example of covalent compounds would be carbon monoxide and water. Okay? Both of those are also covalent compounds. They're not ionic. The smallest or fundamental unit of a covalent compound is going to be a molecule. And so in this case, you actually have individual molecules, which are going to be organized and floating around space and can do their own things. Okay? Has anybody ever seen a molecule with your bare eyes? Usually they're very, very small. Okay? But you all have seen molecules with your bare eyes. I don't have as much of it anymore as I used to, but you all have it on you. It's called hair. Yeah, hair is a polymer. It's a very, very long molecule. Okay? And so they are covalent compounds. Let's talk about naming ionic compounds. Whoops, I went the wrong way. So when you're talking about covalent compounds, that atom's going to form an equal number of electrons that's going to be necessary to complete its octet. The way to draw these out was actually developed by G.N. Lewis, and so it's called the Lewis dot symbol. And it's without his name in it, just called the electron dot symbol. And it was going to be where we use electrons around the symbols of the atoms to represent our electrons in that valence shell. And we're going to join those into our covalent bonds. Okay. You can draw out the electron dot symbol for any atom. It's always going to be the symbol and then the dots for each of the valence electrons around it. You filled in 1 electron on each side, so 1 on each of the cardinal sides, 4, and then you double them up. Okay? And so here we have 3 sets and then 1 by itself over here, right? Because there's 7 electrons total, and that gives you 7. Okay? And so that right there is your electron dot symbol. We're going to join these together, and that's going to give us your Lewis structures for these, where you join them into bonds where they share the electrons. One of the things I want to mention before we leave is do not write these like this. It works very well on typing and printing, where I can have, nice dots and it's very obvious. When you draw them with a pencil, it looks like random scratches on your paper from like a speck. And you go, I don't know what I did. And you'll literally come up to me and like, Dr. Clausen, this makes no sense. And I'll be like, is that an electron? Oh. You're going to be like, just no. Walk of shame. And it always happens every time. Draw the line, okay? That's the bond. That's the symbol for sharing the electrons. So you share a bonding pair is what it's called. It's a pair of electrons that'll be shared between the 2 atoms. Draw a line out to represent that bond. Okay? Don't draw these little 2 dots. You're just going to confuse yourselves. Okay? Okay. You have a wonderful day. I'm right on time. Woo! Okay. Everybody have a wonderful day.
Volleyball tournament this week.
Mhm.
I don't know the official roster that's going yet. But we're supposed to leave Wednesday, which probably, if I'm on the roster, I might be in the class on Wednesday, and I'm also not the lab on Thursday.
Okay.
I'll email you. Want to let you know beforehand.
Thank you for letting me know. Videos for the class, and then the lab, that'll be one of your misdeals, and you'll do the quiz at the end. Don't forget to submit the I'm on the roster to that side.
Yeah.
So in Q, you just like change it, like you give this one to this one, that's all.
Yeah.
So
writing
this
these
one,
out is really
so this one will be positive now, and this one negative.
Okay, so what's happening is you're actually cross-multiplying literally.
Mhm.
So by putting the 3 here, you're giving this a -6 charge.
Oh, so it will be negative, and then the 2 will be positive.
Exactly. So the positive and negative don't flip. You're just equalizing.
Okay.
Okay.
Thank you.
Does that make sense?
Yes, sir.
Okay, fantastic.
How's it going? I had a question about Pearson. So I moved classes, and I saw that I have chemistry 01 and chemistry 02. And I've been doing everything on chemistry 02. And then I saw chemistry 01, and it says that everything's like late, and I think that's what this class is, correct?
Yes.
This is 01?
Yes. Yeah.
Um,
Contact Pearson.
okay.
I'm pretty sure I've had a student before, and they are able to like port it over.
Okay.
Contact them and see what they can do.
Okay. I'll send them an email and see what they say. And then if that doesn't work, do I just come back and just let you know? Because it just shows,
let me know if that doesn't work.
I mean, I know it's not like the end of the term yet, but it just shows like late 000 on the stuff for everything. I saw it this morning. I was like, I know I've been doing.
Yeah, it won't be porting over automatically, unfortunately.
Okay.
Yeah.
All right. I'll send them an email. Then.
Yeah.
Thank you.
Unless they fix that.
Okay. Thank you.
That's one of the perks of being early.
Oh, wait. No, do that later.
Later.
Yeah, sorry. Yeah, I guess. I never reset it.